Hello and welcome to Live Coding with Gerph. Hopefully today we'll be looking at the kernel introspection module that we were working with a couple of weeks ago, and hopefully we'll be getting some completion on it. I'm a little bit tired this morning. Tired, so we'll be seeing how we get on. Fingers crossed we'll be able to do something useful. First though, let's start out by saying where we are and what we're trying to do. So I don't know if anybody new is joining us or whatever, but yeah, so we are looking at the kernel introspection interfaces. Here we go. This is where the introspection interface is. The plan of work we've got is living, and realistically I think we're pretty much at the level of being stubbed at the moment, so we can probably update the status on this shortly. But we have a lot of stubs implemented on this, not actual interfaces. That's fine, don't need to worry about that. One of the things we haven't done though is we haven't actually haven't been able to test the 64-bit side of things, and excuse me. So Alan says that Nitrex says that they can see the monitor screen but no video cam feed. You're right, we've got no cam feed. Well, it's definitely alive, but it's not doing anything. Let me disconnect it and reconnect it. I mean, seeing me is probably not the greatest of things anyway. It's gone. Oh, there we go, it pops up. Ooh, how pretty. I'm very sorry, you've got to look at my face. Gosh, I look chubby today. I think that's just, I'm hoping that's just how I'm sitting and not the effects of Christmas. Yeah, I might be deluding myself there, mightn't I? Right, so, yes, as I was saying, we haven't tested some of the 64 bits. Some bits we did manage to get tested, other bits we didn't. Some bits I think I may have marked without actually checking them. So I think maybe we should have a look at those first and see whether they're actually working. Yeah, that sounds like a good idea. Now, one of the interesting things is we can't get the OSBite bits working because we haven't got vector claims working properly. So those probably won't work right, but we can at least test the rest of it. So let's have a look at that, shall we? Yes, let's have a look at that. So, oh, excuse me. One of the things that we were trying to do last time, a few weeks ago, was this trying to do the SWISE interface. Maybe I didn't actually do it with that. Yeah, don't remember. Definitely we were trying to do that. And the parts of that we were trying to do were getting the testing of that working. So if we have a look in the sources here, so let's just grab you the sources so you can have a look. Oh no, didn't mean to click on myself. All right, stop. Magic porridge pot. Stop. Go here instead. Thank you. That's better. Right. So we haven't got a README file. We should probably put a README in there as well. Kernel introspection. This is where we are. So one of the things we were doing was I was trying to use PIC-OC here. So PIC-OC is a C interpreter, and I built that for RISC OS 64-bit, and we were trying to use that to call system SWISE, but it wasn't working. It was doing silly things and not letting us call things properly. So we do 64 command PIC-OC here, and just do a quick demonstration here. Oh, I want it to be interactive, sorry. I also want to load the module. Load module RM64 kernel introspection FFA. There we go. Right, okie dokie. Yeah, so this is the PIC-OC binary we had, and in theory we're meant to be able to do SWIX and then the SWIGE, the interface call. So if we have a look in Oh, I don't know what the SWI numbers were. I've forgotten the SWI numbers. No, I don't know what they are. Do we actually document them in the module docs here? Do we actually list them? We do. How nice is that? So I want to call read sysinfo 0. So OX58. Oops, OX58. We want to do parameters in 0 because we want to pass in the. Want to get. We'll try and get the data at the screen size. Actually, which one's going to be interesting? Let's have a look at the source code, shall we? So have a look at the source code for read sysinfo. This one here. Which one's this? This is the read platform class. So number 8, and values come out in R0. That's right. So in register 0, out register 0 as well. And we want 8 for the platform class, and then into a variable I haven't declared, so this is result. It'll complain that we don't have result. Yes, we get an invalid operation. So we can declare this as an unsigned int result there. Oops, semicolon. But even if we do that, it comes up invalid operation, which is not very nice. And the reason for that is because it's broken. Simple answer, really. Yeah, the implementation of macros inside PIC-OC is a little bit odd, and it forces things to be integers, to be floats rather than integers. So it doesn't take the natural type; it takes the actual type of the thing you passed in. It's actually everything comes out as a float, which is wrong, but it's not a big deal. So we're going to copy /projects row. Oh, it's not in projects, it's an external, but that's the one, in fact. That one there. Copy that to here. That's the newly built version. If we start the newly built version now, come on. I'm hoping that's the newly built version. Declare a variable and then call the SWI. There we go. And then we can do print out. Can we just do result semicolon? No, it doesn't do anything. I didn't know if it printed out the value if there was if it was just an expression. Result equals print. Wait, as well. Result 0. Oh. Do we actually return platform class? Platform class is unknown. Unknown is that one there. Okay then, that's less useful. What we want is actually the flags then in R1, because that's got a whole load of values there. Let's try that again then, shall we? Also, one of the other things that I did was I made sure that, now we'll prove that it's working, read sysinfo. We actually got the variables in there, so I want to get out register 1 and then print out register 1, and we've got 7f because all of the flags have been set, or lots of the flags have been set. So we now have a way of actually testing SWI calls using PIC-OC, which is quite handy. It means that we can actually check that these things are working in RISC OS 64-bit, which is cool. I mean, this will be manual testing, but we can at least do the testing. So let us pull up the source code for this table. So this is in the RISC OS 64 status repository. And if we have a look in features/module kernel intro, kernel introspection, here we go. A little bit coffee this morning, probably needing more coffee. That was almost funny, but really not. Yeah, you can't make jokes yourself, can you? It's not on this morning either. Right, let's see if we can get a bit smaller and get, yeah, it doesn't quite fit, but it'll do. All right, so Go back to the kernel inspection here, and then maybe we can just start ticking them off. So first thing we can tick off is that number 8 here, platform class, in 64-bit, the stub is working. Cool. Right. Let's try some more, shall we? Let's start with 0. Well, we can actually say that it's working because our value has been printed out here. In fact, why don't we find a couple of results? Let's have some result 0, result 1, and result 2, and then we'll pull out all those registers. 0 to 2, so result 0, result 1, and result 2. And then we can update our little printy thing here. Results. 0, result 1, and result 2. Right. So, read sysinfo 0, read configured screen size, which we have a look at the implementation up here. Squidge that over there, please. Configure screen size, it returns 0. Yay. Okay. Next one is configured mode. Hang on, configured screen size over here, working. If I make the text just a little bit smaller, no, I won't do that. If I do that, it'll slow everything down because it'll have to resize all of my windows, and there's a lot of them. But the next one along is number 1. Ooh, you know what I could do? Int I. For I equals 0, I is less than, how many have we got? 15. I plus plus. And then this is where we find out PicOC doesn't actually allow us to do this as a single line. Should do though. Oh no, I need to actually put it in. I need to print to the print as well, don't I? So I'm gonna. It should support this because it's not like it's non-standard. There we go. It's that line there. Copy paste. RSI number %I. Oh, I missed my brace. Ooh, that's quite cute, isn't it? That's really quite cute. I like that. Actually, it was quite interesting how the code actually executed the first iteration and then stopped and then went back and did the others. That's actually quite nice interpreter. However, look at this. We've got 0 out for everything. That seems wrong, doesn't it? Why does that? Where have we got 0s out for everything? It's not very nice. I wonder if it's optimized it wrongly. That might be what's going on, or it might be my code's wrong. Don't really know. Unassigned wrong. Result 0, result 1, result 2. Let's just see this. I mean, it might be that we did that there's something up with PicOC again, and when I need to. It's already defined. I know it's already defined. I was hoping that we'd be able to. Oh, I know what I'll do. I'll just exit and restart it. I mean, this is not because it's in a different scope. It should be okay, but oh, I need to declare int I. Just try this. Brace. No, it's coming out as 0s. How odd. Right. In which case, oh, yeah, I am calling the right system call. Yeah, I think there's definitely a bug somewhere in there. I don't think that's my code. If anybody can see a bug in my code, please say. But it looks like that's not working properly. So what instead we will do is we'll just go and do them manually. So 0 we've tested. Number 1. System goes out of scope. I think I've got it confused. Maybe this isn't such a great interpreter for doing this with. I mean, that's something I may need to consider. Right, yeah, 0, result 1, result 2. Okay. Course Y for that, and then print out the results. There's my print statement. There we are, print results. How odd. How odd. I wonder if this means I've got me out R wrong. Oh, that would be really dumb, wouldn't it? Out 0 or underscore. It maybe could be I've got the macro wrong. 1 or out 2. Oh dear. Oh dear, that is very embarrassing. So underscore out equals not percent x underscore out r 0, 2 just x 0. Yeah, that's not right. That's not right at all. That's why it's not working. Okay, so I can go back to my loop again. See, now we're learning all sorts of strange things about my inability to write code, which is always handy to have. Right, here we go. I've just got out 1. So in a normal circumstance, I would go off and now pick OC, but I'm trying to focus on one project at a time and not jump between them. Why isn't it like I? Okay, there you go. Result not is already starting. Int I, print them all. Go on. Oh, and I missed my brace again. That looks more like it. Now, interesting here, we've got these are generated errors. They've returned error blocks, which is why they've got those same values there. Ooh, different values actually. That's probably not recognized and that's not implemented, I suspect. We'll see anyway. Right, so what we got here. 0 has returned zeros. 1 has returned 1b and 7. 1b is 27, which it is indeed 27 up here, and 7 is correct. So chips and unique ID should be returning a number of different chips pretending that they're not there. I think we were just returning none, 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 undefined, none. So we got FFFFs at all of that. That looks good. Number 3. Number 3 is this one, Ethernet address. We haven't got a MAC address, so that's okay. We've just returned zeros. Yes. Oh, that's interesting. Oh, we've actually returned not implemented. Well, actually, that's strictly correct. I think I'll leave that because I think that is actually working. It's just not working very well. 5. Raw unique ID is a unmunged version of that, and that's returning a one. I don't know. A unique ID of 0 would mean it's not valid. So I don't know what a modern system returns for those. Be interesting to see what modern systems do return, because it obviously depends on the hardware and the like. So, but anyway, yes, we will need a call to be able to read that. Kernel values. Now, kernel values just aren't going to be implemented at all on 64-bit, but they will be on the other parts, on the other 32-bit version of the system. So for now, not implemented. So 6, not implemented. Read system info last abort. That's going to have not implemented, but we'll be able to put some values into there. Platform class is 8. Yeah, so that was the one we had the masked values for the different values in there. That's good. ROM information, we just don't have any in here. We could probably do some with that, actually. We could probably do something with it. Number 9, yeah, not implemented. Read OS version, again, not implemented. Debug information, not implemented. Read, and this is the actual top level call. Okay, so we can say that they are all stubbed all the way down to whatever that one was, 11. So yeah, let's have a go then. So update, mode work, definitely, we definitely saw values out of that. Did we see values out of that? Chips and unique ID, number 2. Yeah, we got values out of both of them, that's okay. Ethernet address, return not implemented. I'm going to leave that one off for now, just because, and that returns zeros, which was kind of valid. I'm going to say that that's stubbed because in 64-bit it is exactly right. Last abort stub. That returned, it's as good as the 32-bit version. Yeah, these are all stubbed. And then we're down to these ones. Okay, which aren't implemented at all. Okay. So let's have a quick look at read memory size, physical table size. That should be returning a 0, apparently. Give me a Swix call. That out R is bugging me now. It almost certainly means I've done something really dumb. Also memory 6. Also memory is out of scope. So that's kind of interesting. I'm not sure what that means. Hash include size H. It's out of scope. But it isn't out of scope. It's, oh, I don't know. Maybe there's a, maybe because I did that loop it got it confused. I may just have to do something about that. Oh, define some variables, shall we? Variables. Because remember, C is normally expecting to be in a main function. So Spanners has said that Outar's got a bit of bit spreading magic in it that's probably a bit brittle. It probably is, and I may have broken it myself. I may have done something really dim as well. I have a feeling it might be that it's relying on 32 bits. And it's running on a 64-bit OS. That might be what it's doing. So it's clearing, because it clears the bits at the top of the word. That's probably what it's doing. Right. We'll have a look at it later. Or maybe I'll look at it in my own time. I don't know. We'll have a see. Results. Here we go. So OS memory 6 returned as an error. Let's have a see what OS memory 6. Yeah, return not implemented. Physical table size, also all of these are returning not implemented. But they are going through our stub code here, so I'm going to go and just tick them just for the heck of it. Because the 64 interface is working as well as the 32-bit interface. And if it's working as well as it, I'm going to just say it's good. MMU features, we don't support that one. Yeah, we probably want to, but I haven't got it just yet. Cache features, let's just check that one, shall we? So that was, sorry, I've forgotten already. Platform features. Platform features. Get the letters around the right way. 0. That looks an interesting pattern, doesn't it? 804.04.001. So where's platform features? There it is. So what did we return for this? Oh look, we've got our magic table there as well. Oh, I was going to convert that, wasn't I? Right, so in 64-bit, so approximately for 64-bit, we've got this correct. Invalid reasons are safe, no physical pages, cannot disable decache, and code areas required, synchronized code areas required. So that sounds good to me. Yeah, it looks like we're actually doing the right sort of thing there. Yeah, we can say that that's working as well. MMU features, I think we said we don't support. MMU features, yeah, it just says not implemented. But strictly, you see, it's implemented to exactly the same level at the moment. It's stubbed to not do anything. We haven't got the other ones in there, the cache features. Yeah, we have got cache features. Oh, look at that. We can do something with that. All right, let's try that one. Cache features. Sorry, I've forgotten the number already. Cache features. Oh, 33. It's on the screen. 33. Or I want register 1 as well. 0 for cache level. Cache type no, for cache level 0. And we say type 1, which is we have an instruction cache. And then we go to level 1, and it tells us we have no cache there, which is what we expect. Oh, there's all sorts of other values in there as well. In R3 and R4. That's quite nice. Okay, cool. That is working as well. MMU features is ticked. Cache features is ticked. CPU features not supported yet. We'll have a look at that some other time or leave it. And then CPU registers is supported but comes out weird. So we'll just quickly check that one. That's 64, isn't it? Yeah, 64. Yep, 64, and that has a table there. Which we can't actually see because, oh, actually we can see, can't we? Unsigned long star data equals unsigned long star OX900B7B8 printf value long so data bracket 0 and then bracket 1 and 2 and 3. Do those look right? 1 4 1. 1 should be the architecture. 4, I don't know. It'll be defined up here. That's the 32-bit form of the table. And here's the 64-bit form of the table. 1 4 4 1. Well, that's interesting. It said it was 0. You know what I think? I don't know what I think. I know what I think. I'm wondering if long, inside long is 64-bit. So 0, 1, 2, no. Data. Yeah, size of data bracket 0. Oh yeah, that was a bit dim. 8. There we go. So that's why I would need to. Hang on, data. Oh, I've accessed the same thing. There we are. So if I actually change my code, there we go to data W. There we go. 1, 2, 3. 4, 5. There we are. That looks more like the table that we've got there. All right. So that's working, which is something that makes me happy. And I can happily say that that is now tickable. Oh, and learning little bits about how I can do testing with PicOC. It's still a little bit, I'm getting used to it, but we'll get somewhere with it. Okay, so what have we done? We've really just verified some of the interfaces we've currently got, which is a good thing, and I think worth doing. So let's go and make sure this is actually committed. So I've got my status up to date. Diff. Yeah, there we go. I put lots of X's in there. Commit. Where's a added results of testing the introspection stubs. Returned values as expected. Cool. And then I can push that up here, and we can have a see just to feel. Oh, I could have updated the stub. It's a stub level. Oh, it didn't push anyway. Since it didn't push, let's update it to stub level. Status.md. Oh, kernel inspection's here, and we're going to change this to stub because I'm happy with that. There we are. Thanks. And we'll just append that to the last message, I think. The stubs are now complete, so I think we can update its status as well. There we go. Right, now first we need to pull in the changes that have happened offline and then push them back up again. So previously we had a 25% functionality and 50% vectors because of it being stubbed and only half the code being there, and 31.7% total. So if we just reload this, fingers crossed, we should see something a little better. And of course we should see that stub appear. Reload, 40% functional and stubbed. Not quite at the point of being a prototype yet, but we're doing okay. So what shall we do now? What did I say I was going to do? So I could generate this table. This table here is a bit of a awkward one, isn't it? Because it looks pretty ugly. We can't really see what we're trying to do with this. So it'd be nice if we could generate this as a proper table. And we've got some C code, some Python code that can do that because it's in RISC OS Pyromaniac. So should we give that a whirl? Yeah, I think we can do that. We'll just have to see how it works. So do I want to lift that code now, or do I want to do it on my own time? Why not? Let's give it a whirl. It's at least it'll tidy up a bit of this ugly code in here, and we can see how we generate this stuff. So I'm going to need to go back to here and just check that we haven't committed everything. Oh, we haven't. Oh, what's this? Run on build service. What have we done here? Oh, that was from my testing of PicOC. Apparently I made the changes to the wrong file. Whoops. Let's just have a quick look at that, because I think some of that's actually good changes. That's in build on build service. Run on build service. There we go. That one there, please. Have a little bit more of this space. Right. So yeah, we want to revert that back to running the module. But if you look in here, what we've got here is a list of modules. So actually, kernel introspection goes into the modules. kernel introspection like that goes into modules. And we want to put this back to being bin/star C and test data. There we go. So that's the module files that we'll load. Okay. Actually, the module files is without the FFA there. But we didn't add it to the list of files that we need to archive. That's odd. Files, we should add it to the files. So if we just skim down here to where we load the modules, what we can do is do files plus equals module comma, oh no, module comma FFA, so that we cause the module to load. And then we don't need to put the modules list in the zip because we've already appended it to the files list. I think that looks okay. Yeah, looks all right. Shall we see if it works? To see if it works, we make tests. Oh, there's an example there. Just run one of the tests. That sounds like a good idea. Does it work? That doesn't look like it worked, did it? That really didn't look like it worked. Less.row build. Oh, did we not leave the file behind when it fails? Yeah, we delete the build file. Let's just leave the build file behind. We'll see what comes out. Yeah, we didn't load the module. If we didn't load the module, it's not going to work. So how do we not do that? Boom, boom, boom. Modules equals kernel inspect. It's telling me modules appears unused. Ah. So does that mean? Oh yeah, because I called it module there, not modules. Ugh. Okay. Try the test again. Yeah, passed its test now. And if we have a look at the build file, yeah, we've got the RM load in there. So we're all good. Okay, so we can put that to there. This is just a nicer, we've tidied up how parts of this code work. Not much, but a little bit. Tidy up the build service runner. I'll just load from the general files list and loads those modules to start the test. There we go. Ta-da. Okay, let's push that. Hi Arctic. All right, push that. We are now set on that. I think we've got tests that are working. We've marked ourselves as a stub, so strictly I'm complete on this, but I do want to tidy up that code. So as I mentioned, we have in platform features here this big table of data that's pretty ugly really, and we want to generate it automatically from something that's actually readable. So I've got a code for that in RISC OS Pyromaniac. So we're going to go and try and steal it. We're going to try and steal it. I can't. We'll see. So where is it? Tools like projects, not that. Pyromaniac. Somewhere in here. So it'll probably be in the emulator section. Base. Is that where we're going to be? Or is it part of this, or is it part of RISC OS? I'm not sure. It doesn't look like there's any code to convert things in there. Or is it registers? I'm not sure. It's probably in registers, isn't it? Because that's more likely. So get rid of that and have a look in registers. Here we go. This is a definition of a calling convention. We have backtrace operations. All very clever. This is how we do a backtrace for things. And it's different between different architectures. Architecture registers, this is them. This is the thing we want to pinch. Architecture registers, that's a definition of a register mapping. This is a definition of a flag. Preserve registers, no, that's not something we want. And this is the actual architecture register definition for 32-bit. And if we search down here, we should find the same thing, but for a 64-bit. 64-bit implementation of backtrace, and then registers for, here we go, architecture registers for 64-bit. Right, so this is the bit we need to, those are the definitions, and then we need the thing that walks it to generate the table, which apparently isn't in here. Okay, well that's not a problem. So let's get those. Easiest way to do this is to just create a new file in here. New file. Stop it. In here. New file. Called. Oh no, not in the C file. Sorry, in the top level. Build CPU registers.py. Register definition. Yeah, that'll do better. That's a better name. User bin Python. Build the C sources that define the layout of registers in the exception, well, register dump area, because it's not just for exception. Okay. Taken from RISC OS Pyromaniac and butchered. I think we'll say that. Yeah. Okay, so let's grab some of this code. So we've got the class arc64. And it has, here's the architecture registers for 64-bit, all the way down to a little bit further. There we go, that's those. And then we've got the same thing for 32-bit. Class arc32. And if we define one for a different architecture, it will be another type, another object. I wonder if we should really have these as based on other things. We want these definitions here because that defines the different structures that we're going to put in. and then we want the one that defines, here we are, this defines the architecture registers for 32-bit. So we've pinched the right bits of code so far, just for the definitions. I'm going to just quickly go through what the definitions are, so give it a little bit of context to this. Right, oh sorry, let's do that again. There we are. Right, so we also need some other bits as well, don't we? We need to know the architecture number as well and things like that. Well, I'll define that separately. Okay, excuse me. So let's look at the definition first. Let's just start with the definition, which is in this one. This one, here we go, yeah. So this is the table. It's got, first it has an architecture identifier that says what type of data we've got in the that the system's using. Minimum instruction length, maximum instruction length, which for the processors we're working on at the moment, they're the same thing, but for other processors, it might be different. And then the length of the register block itself. And then all of that is then followed by a number of different definitions. So there are definition types for registers themselves and for the types of registers. So firstly, we've got a register identifier. So this is an internal identifier that says what they are. Just for ease, that's how we've defined them. They may not map to actual register numbers. No typo, that should be capital A on the second bit of that. Doesn't matter. And then type 0 is this is a register, and then we've got some flags there that says this marks as being the end of the list, just to make it nice and easy. We've got an offset from the start of the header block that defines the string that contains the name of the register. Hang on a second, snooze please. Yeah, that's okay. Yeah, so the name of the register, that's going to be R0, R1, R2. And then we've got offset from the start of the register dump for the register data. So that'll be at offset 0, offset 4, offset 8, and so on for 32-bit registers. Then we've got some flags that describe what the register is. And the register can contain different things. So it can have the general purpose register, it can be a stack pointer, it can be a link register, it could be the program counter, or it can contain state flags. There's also possible we can have other things in here. So we might have, say, definition number 5 being floating point register, and then maybe a long floating point register and things like that. So we can start doing things like that. I'm not quite sure how we're going to do that, but since I haven't decided, I'm leaving them alone. We'll work them out later. We define what size the register is because some registers may be different. So in ARC32, registers are always 32-bit wide. Fair enough. But if we were to look at, say, 6502, which is the old BBC processor and Commodore 64 as well, and I think the PET used it as well, actually, come to think of it. Can't remember. But the Game Boy used it as well. Yeah, I think the Game Boy used it because I think Game Boy Advance was an ARM. Anyway, regardless, in the 6502, the A register is 8 bits, the X register is 8 bits, the Y register is 8 bits, the stack pointer is 8 bits, but the program counter is 16 bits. So you've got this little difference in there of how these things are handled. Also, the stack pointer isn't actually a stack pointer, it's just an offset in 6502, so that's all different as well. yeah, and then if you were looking at things like x86, you'd have registers that were different lengths as well. We'd also have to probably define that things weren't general purpose registers, but they were segment registers and things like that. Let's not try to think about x86. x64, a little bit better, AMD 64, depending on how you look at it, would be different, and we'd have some better controls on that, a better understanding of those. But yeah, so these are the way that we define what the register type of register it is, and the size as well. And the reason we define the type is so that we can put special criteria on those things. So if you wanted to find the program count, yeah, all right, I'm going to snooze. Let me just cancel my break time, disable for a couple of hours. Yeah, so we might say you wanted to find the program counter in there, or you wanted to find just the link register, return register. So those you could find in there. And there might be special ones like link registers for special modes and things. So you might need some special casing in there. But you'd be able to maybe put them into groups as well. Anyway, bit alignment of the register value. So this is so that certain registers can only take particular values. So in 32-bit ARM on old processors, the general purpose register, the stack register, the program counter, and the link register could have any values. In a 26-bit environment, not 32-bit. In a 32-bit environment, the program counter is restricted to be word aligned. It has to be aligned to 4 bytes. And the stack counter could be anything. Stack pointer can be anything. It won't necessarily work because you want to use it in certain ways, but the architecture doesn't place any requirements on the stack pointer. Now, when we come to later versions of the ARM, the stack pointer is required to be aligned, and it's required to be aligned to, I think, 8 bytes or possibly 16. So you would have a different alignment value for that. And the same goes for ARC64, where it must be 16-byte aligned. So that's why we've got the provision for this. And then we've got a final set of flags in the end of there that are reserved at the moment. So we haven't defined anything of that. And we will do so at some point in the future, maybe. So that's the general way of doing things here. Excuse me. Yeah, there's also a number of things for definitions of bits and the like, which we can actually have in here. So if you put in here, you can define what bits inside flags mean anything. So in the state flag, so in the CPSR, the program status register, each of the bits means different things. So there's the V flag that means overflow, there's the carry flag, there's the V, C, negative, and I've forgotten. What's the other one called? Zero. Yes, that's it. Z. Sorry. Oh, dear me. Brain went completely blank there. So you can define the bit number within the flags, value described. So you can say what value you're describing in there, and then you can give it different enumerated values. I'll show these when we get there, but they're a little bit more complex. And this allows us to get more information out of the table and to be able to decode it. So, as you can see here, for the register, I have defined some of these things: the exception offset, the bit width, the name, synthetic. Synthetic mean? Not sure what synthetic means. Might mean that it's an internal one that I don't need to actually keep for now, but we've got it anyway. Yeah, I'll have a see about that one because I'm not sure at the moment. And then you've got the register types, which are actually in the Python code, just letters, because it's easier to read. So there we go. And then for the registers, for the register flags, sorry, we've got similar information here that describe things. Again, I'll describe that a little better in a moment. This is the actual list of values we're going to put into the table. So we describe a register, so we describe all of the registers here and give them internal numbers, internal names, and their width in bits, and where they're stored in the exception dump, and their type. And as I've said here, we've got the program counter has an alignment of 2, so it's got 4 byte aligned. And the CPSR is a flags register, processor flags. Yeah. And then we start describing the flags. So here we go. This is how this works. First, we starting by defining what the mode is. So the mode is held in the lower 4 bits of the flags. And it has a number of different values which are enumerated here, and we're describing what those values are. So this says this is what the header is, and this is what the values that value can take, and we define the last of those there. And then we start to describe whether it's 26-bit or 32-bit as the next bit in the CPSR flags, and so on. We keep defining these values. It's not particularly complicated, but that's how we define them. These flags immediately follow the thing that it is describing. So you describe the register, and then you describe the flags for that register. And I've also set down here that the SPSR is present, and strictly that's another copy of all of these. So we could define that here, but I haven't done. It's also not actually stored in the register dump, which is why it's not listed there. Maybe in the future we might do that, but that's not the case right now. Okay, so that's 32-bit. If we have a look at 64-bit registers here, we've got all of the registers defined. Again, these are being defined with internal numbers, and we've got the processor state here, which is again described as being a flag. The stack is defined as having bit alignment of 4 because it's got to be 16 aligned, and the bit alignment for the program counter is again 4 bytes, bit aligned to 2. Now we've also got here the processor state flags. These are garbage. Those are not strictly true anymore. So not really meant to be in there. This is the exception level, which is listed in there. Again, bitness, you can describe whether it's 32-bit or 64-bit mode. That's sort of processor defined, so you might actually want to change that in the future. The actual definition of the table might be different. And then we've got some other flags in here that are set. We haven't defined any vector floating point registers. We're going to leave those alone right now. Okay, so that's what the tables mean. So now we've got to find the generator for it. And I can't remember where the generator lives. I'm assuming... I'm not actually assuming anything. I don't know where it lives. Let's have a look, shall we? In RISC OS / well, looking at all of RISC OS. So have a look for SWI's platform features. There we go. Register dump info. Here we are. This is the thing that generates that table. That's the entire code that does it. So let's lift that. This is a class that just does all of that work for us. So I will work through it. It's okay. All right. Bum, bum, bum. Right. So this is not a resource here. So resource in Pyromaniac terms means thing that you can reference from elsewhere. We don't need that. We don't need it to be initialized with a RISC OS structure. Although I'm gonna have to see how we're actually using it. So we created dump resource for each of the different types of structures. This is the thing that generates the descriptor. So really we want to do is we want to pass in one of these objects. In fact, we could probably, we'll pass in arc object. So let's do this. Arc here. We don't need that, but we do want to define it as arc. There we go. This is just for speeding up the generation. We don't need these. I just call this a registered dump info. It's not a resource anymore. We don't need to cache it in this instance, I don't think. Oh, should. Yeah, let's cache it. What the heck? Then we don't have to generate it repeatedly. What the heck? Right. So the descriptor size we can work out. We know how many, the length of the architecture registers times 4 plus times 16 plus 4. The string size is the sum of all of the string names in there. That's quite clever, isn't it? And then we want to create some memory. So let's do an are we allocating words for each of this? Yeah, we're allocating words, and then we're doing a write word. So we'll just create a very simple memory accessor function here. So this is, we'll call this memory. Write word. So init. And if we use this allocator function, so we want the size of it. Self.size. All of this is going to be a list of, it's going to be words and, oh, we have some strings in it as well, aren't we? Because we're going to write the strings at the end of it. Where do we write the strings? Do we actually write the strings in this? We must do. Dump size goes into there. Strings. Ah, yeah, descriptor string offset. Oh, that's how we write it. Oh, that's fun. Yeah, we might change that to be a little bit less Pyromaniac-y. Size equals size. Okay. What I'm going to do is I'm going to do a list of size words equals a dictionary of words. And to write a word, we go write word value offset self. There we go. Self.words bracket value offset equals value. Oh, I'm not doing well on writing code today. And then we'll have another one that does write string value offset strings value strings. Okay. Dum, dum, dum. So I'm aiming to do here is to build a list of what words are going to be and then the strings, and then we can write out all the words first and say these are words, and then at the end we'll write out the strings as strings, so we're not actually losing the data of what type of data they are. What we can do here is, instead of putting this in here, we can do the architecture arc num. We're going to have to call that, aren't we? Because arc is already a thing. Arc num equals, I need to pinch that value, don't I? So if I have a look in here, constant OS platform, there we are. Here's our architecture things. Oh, and look at that. There's all our values that we're going to want to use as well. Oh, look at all this lot. Isn't that cool? We're going to want all those. And we're going to want them in a thing called OS platform features. So why don't we just put them in a file, OS platform features, and then we can import it like we did in Pyromaniac. That would be easier. So if we do a new file, OS platform features.py, there. It's not an automatically generated header, we'll just put a comment in here. Constants for OS platform features on. There we go. So in here we can just do import OS platform features, and then all of our definitions should be the same as they were. Arcnum equals arc.arcnum. So this would make it a lot easier for us to work with. So arcnum equals, oh, that's the wrong one. Oops, 75, no, 64. And then the same goes here for 32. So now we've got no special cases in here, and we can write those words. We know what the dump size is, descriptors. If we're writing a register, then we put the register type in there and the number, name offset. Right, this is where we write the strings. So I want to do write dot write string at string ar.name at offset string offset. I'm sure we're going to have another one, so do x exception offset, a little bit of debug code, dump size, CPU registers. This is building up the different flags words there, and then if we're building this malformed register descriptor. Ah, right, okay, so there's an error in the table there, and this is where we write another string at str offset, and it's ar.name. There we go. And now we've got a descriptor. The descriptor is allocated here, so we want to create that as a memory of length blurb. And I think that should be vaguely right. I mean, it's probably not completely right, but we'll give it a whirl. So move this one out of the way. That's in the way now. Okay. So the actual table was just something that was created in RISC OS Pyromaniac, and you can have a look at that if you want when we push it. Right now we're just going to try and generate it. How does this work then? So we want to create a arc32 object. And then we want to create a register dump info object using that RDI32. Oh, that's not quite RDI. RDI is the name of a register on x64. CPU reg. There we go. CPU reg. We'll keep it as register dump info, but yeah, we'll do that. And then at the end of that, we can have a descriptor 32 equals CPU reg 32.32 descriptor. Okay. Should we run it? Python build yeah, that didn't work. And then expected it work. Oh dear. Oh yeah, I didn't delete enough of it. Now, if I remember rightly, I should actually be able to do a Python run here. Oh, I can. Arc32 is not defined. If I press F4, I now need leave the editor. How cool is that? Done. Whoa. Although actually now I want to leave the editor because I want to do this in interactive mode here. Right. So if I look at oh, sorry. Descriptor 32. Oh, hang on. Yes. Call the function descriptor. Then we can run it. Oh. Oh dear, here we go. Right, okay. So yes, it didn't work. I'm going to need to have a look at this a bit more. Let's run it again. Register dump info, I had no variable that, which is here. Because arcreg is the thing that we're actually passing in now. Oh, we should have called it arcregs. Yeah, we call it arcregs. Oh. No, arc.arcregs. Arc.arcregs. Yeah, that seems probably like it. Arc is not defined. Where? Oh, because it should be self.arc. There we go. Oh dear. Oh no. I use these. Oh. None type has no. Descriptor? Why is descriptor being none? The descriptor was assigned to a memory. Oh, because I defined it as a def, not a class. Oh dear. That's very confusing. I'm surprised it didn't tell me about that. That was rather silly. Oh, and I use this syntax here to be alias an offset. Oh, that's frustrating. That's kind of frustrating. Is it frustrating though? Def base offset equals 0. Self.base offset equals 0. Oh, this isn't going to be quite silly, I think. I know what I'm doing, it's okay. I'm just get item. So get item is called when you do a square bracket dereference of it. Is it get item? I think it's get item that gets called. Index. So this should return a memory alias. Memory alias for this object, which has a base offset of index. Yes, and now we'll define a memory alias, which we will define in terms of a memory. Init self. Oh, come on, self. And then a base. Oh, sorry. Base object and base offset, which must be given. base offset equals base offset. Self dot base. Actually, you can also make that 0. So if you write the first word as well, you can do that. Base offset, base offset. Base object equals base object. Self dot size. Oh, I should really call the super, shouldn't I? Super self memory alias. Bracket. The size is going to be base object dot size minus base offset, and the base offset is going to be base offset, which means you don't need to set base offset, you just use base object, and the size has already been set. But words can be base object words, and strings can be base object dot strings. QT. I think this will work. It's feeling a little bit like a bit of magic, really, but I don't want to see type, not alias. Did I do that wrong? I don't know what I did wrong. Memory alias for self of type base. Super argument 1 must be a type, not a memory. Oh, I got them the wrong way, that's why. This is where Python 3 is a bit nicer, because you can just call super as it is. But, sorry, wrong window. Just thought I was being, he was calling me cute. Oh well. Init exactly one argument. Object. Oh, because that's not a memory. It should be a memory there. And then I've got another one that I got wrong here. So let's see where we put row in there. Arc.arcregs. Okay. Has no address. Address is the equivalent of base object, a base offset. So actually I could just change it, couldn't I? So base offset became address. Base offset is now address. Find, replace, replace, yep, 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 yep. Okay, good, run. Didn't fail. Oh, excuse me. Oh, that was weird. It did a bounce up and then bounce back again. I don't know why. Oh well. Descriptor 32 is a memory object. If we look at the words, we have a list of all the words there. And we'll look at the strings, and they should start at 788. And start at 804. Ooh, that's interesting. Ooh, because that extra entry is. I don't know why that is actually. That should have started at 788, not 804. Why did they start a bit further on? Did we miscount? I mean, it might be that the original code is all wrong as well then. 16 bytes for the header, 16 times the length of the architecture registers, and then a 4-byte offset. Ooh. That's not right. I've written this to the wrong place. Script to bracket 16. Does that mean that we're writing to the wrong offset there? Not that code, this code here. Address equals 0. Address equals 0. Address equals address. That's what we should be doing there. So if I rerun it now and then do the words, ends at 800 and the strings should start at 804. Yep, there we go. This is quite nice. This has actually worked out quite nicely, I think. So now we need to turn this data into something that we can actually build into the C code. So let's do that, shall we? In fact, we'll do it in the memory code here, because then we can actually do C code. Ah, what the heck? There you go. Right, so we're going to have a list of lines. So lines equals bracket bracket. How am I going to do this definition? Because I want it to be like nice and readable. Don't want it to be like messy. Well, first we're going to write out all the words. So what we'll do, I'm trying to think of right. So how would I represent this normally? So what I'd like to do is something like type def struct CPU registers. Yes. So this is going to be a register uint32, a list of words. So this is the words here, and there are so many of them. And then a list of strings, which is a single string in line with it. This is the string data. Strings. Bracket bracket. No, we should probably define it to be the actual length. We have to define the actual length of it, don't we? Because you have to have something concrete there, like that. CPU registers. And then you define CPU 32. Registers equals brace, then a list of words, so we can write down all the words here, and then the strings, which can be R0 / 0, R1, like that. How's that look? That looks kind of okay, I think. I think I'm going to do it like that. So let's have a see. Paste. I don't know why I did it like that. That was moving it up one line. Oops, didn't mean to do that. Edit every line. You know. Okay, we'll take the gap out as well. No, all right. Lines dot append. Use single quotes, then it won't confuse us when we're doing the double quotes for the C code. do here is we have this. And then in here we want to write the number of words. So we can know the number of words because n words equals max of all the keys. So self.words.keys plus 4. Ooh. Word type word type, and the other one is the n words. So we also want to know the word length. So that's the number of words we're going to be storing. Word type and number of words. Cool. Yeah, looks okay. And then strings is going to be very simple. This is going to be interesting because it's the string is that strings key. So that's the highest string, and then the highest address is going to be highest string, yeah, plus how long that string is. Strings bracket highest string the length of that plus 1 for the extra terminating byte. String bytes. Right, and now we need to write out all the words. So for that, as we do for offset in range 0 to n words, value equals words.get offset times word length. If it wasn't found, we're just going to put out a 0. Not defined. And then here, else, lines append. Ooh, too many. Long indentation there. That was a bit weird, wasn't it? OX. We'll put in there the value. Dum, dum, dum. And now we've got to do the strings. So we do for offset in range in. Oh no, this is going to be a bit different, isn't it? Because we've got to actually write each string out in order and any padding that we may have accidentally added. So let's just, because there might be some padding in here. I haven't put any in, but it should be. Offset equals n words times word length. We know we're at the end of there. Dum, dum, dum. So this is actually, think about how this is done. So I want to start from there and I want to step forward in each of the strings. Yeah, this is definitely more complex than my brain is wanting to deal with today. Okay, while string base equals there. Okay, offset equals 0. No, end equals string base plus string bytes. Yep, there we go. Offset equals string base. That's where we are right now. Yeah. While offset is less than end. Good. String equals self.strings bracket dot get offset. Get the string from that offset. If string is none, if there wasn't a string there, I'm just going to put a padding in there. Otherwise, and also offset plus equal 1. Otherwise, we put the string in. And that is string, like that, and then do offset plus equals string, len string, sorry, plus 1, because that's the end of the, and then we can return the lines. Can't use a bigger raw string. Oh, I did mean without that. I did mean it as a single raw string. I was meaning it as a single raw string. So let's see if it works. I hope this is what you were meaning. Oh no, I can't write code. Oh, you were, sorry, I wasn't paying attention, Dave. I apologize. I've been woefully absorbed in my code. Right, so descriptor got, if we do C code here, what do we get out? Oh yeah, uint 32t and 4. Doesn't look like that worked, did it? Does it? It looks like I got out a lot of rubbish there. Oh dear. Well, the words seem to come out okay though. These seem to be sensible. But then the strings just, oh no, hang on. Oh, that's interesting. Yeah, so strings seem to be looking okay. It's just they've gone on and I've got way more than I expected. Oh, that's a pity. Why have we got so many? Why is it in string base plus string bytes? Oh no, it should just be, end is just string bytes. Oh. Words end is that. Word size. So string bytes is that minus word size, because that's the actual thing, and then string base plus. I think that's probably more like it. Yeah, I haven't explained this very well, I realise, but we now have a bunch of C code. Oh, except for that. Minus 001. That's not quite what we wanted, is it? Actually, if I do this as and 4, 5, 6, 7, 8. If word length 4. unsupported. That's not going to happen because of how we've written it, but just for now, close that. Let's see if we get it this time. There we go. Got my nice one isn't coming out there. Much better. Okay. It looks kind of like a structure that you might want to use. I mean, strictly we can do the same thing again with the ARC32 one. For 64, I mean ARC64 one. Definitions there, so that gives me the C code for that one. And if we do it for the 64, which is also going to use the 32-bit values, yeah, that looks okay to me. I do not feel bad about that. Hopefully that's the same structure. 248 bytes. Looks probably about right. Ooh, interesting. Yes, that's a good point. Whilst I'm looking at it, I noticed that I haven't made this a static const because you shouldn't be modifying it, and I don't want it to be exposed outside of this unit. Actually, we do want it because it's going to put them in different files. I'm going to put them in different files so that we can include them as necessary. Right. So I didn't explain a lot of that very well, but hopefully it was vaguely understandable that we've turned this list of this table of values into a static table that contains offsets and descriptors of the values that are being used. I mean, in theory, we could actually include comments with these as well. So we could actually make the add word, write word, take a description and put a description on the end of it as well. So we can actually do some clever things there. But for now, I'm going to say that that's good enough. I'm going to take a short break, and then we're going to come back and actually write these to files and then start using them inside the CPU information code. And hopefully it'll work. I mean, yeah, that's the plan. It's a bit of a long-winded thing. I'm really sorry for it being a bit odd, and honestly I think that this memory and the memory alias object, I am quite pleased with that. It came out right, but it was sort of a bit of a inspiration at that moment of, ooh, this'll work. Yeah, okay, break time, get some drink. Maybe grab some chocolate, I think, to give me a little bit of a wake up as well. And I'll see you in a little while, probably about 10-15 minutes, about 10 to maybe 5 to 2:55. Yeah, there we go. All right, see you in a little bit. Hello, we're back. Oh dear me. Right, I am still not awake properly, but at least we're here. Oh gosh. Just feel very, very tired these days. Well, today specifically, which may have had something to do with general news over the past couple of days that have been tiring. Yeah. Anyway, I have a new mug. This is my present from my wife for Christmas. She got me a little Compiler Explorer mug with, there we go, the instruction, the register assignments for ARM, which is quite cool. Specifically, this is the ARM 64 one. So yes, that's cool. And of course, I'm sure you're all watching Matt Godbolt's wonderful compiler optimizations series over Christmas, which was a lot of fun. Also, it was very fun watching the outtakes as well, and seeing how much he made a mess of things and made it look good nonetheless. It's not very tiring, I imagine, doing that. But yay, well done. Cool. So, what have I done so far today? Not a lot, really. I've verified a bunch of the interfaces are working, and I put a little bit of code together that generates these tables that we were talking about, which are not very complicated, but they give us the information we need to be able to decode the my brain's gone. Exception dump tables, the CPU register tables. And from that, we've got now some lines that will go into a C file. So what we can do now is we can actually generate them. So we want to do one for each of these. So def generate C file. ARC32. Actually, we can generate it from ARC30. Ooh, no, that's not it. From an ARC32. No, try this. From an ARC object into this file name with a name. So ARC name. Oh, actually, the ARC name could be in the ARC structure, couldn't it? That'd be good, wouldn't it? So we can actually put them into the ARC32. Could have a name in there of the ARC32, and we do the same for the 64-bit one. So that's a bit easier. File name. And no, that's good enough. Okay, so we've got the ARC, so we don't need that. We don't need ARC32. We need to do ARC there. CPU regs. This is a generic version. This generates as a descriptor, and then we can generate ourselves some C code from that. So C code equals descriptor.C code. Now with open file name for writing. Writing has a W at the beginning, not an R. Of course, because that's English for you. And we want to write into it fh.write auto-generated CPU registers for syntax arc.name. Actually, we want a header as well, don't we? Because we'd like to have a header that describes what they are. It's a C file name and header file name. There we go. That's what we'll do. Okay. Architecture name. And then for line in fh dot in C code fh dot write. There we go. That's the lines, and that's the C file written. Now I want to do the same for the header file. Actually, we could just call it H file, couldn't we? C file and H file. That would be a bit more nice. C files even. Yeah, we'll pass in a H code. Do you want to have one that generates a C code in the header? Yeah, because if we think about this, I also want to do the var name as well, because this here, CPU register, blah, 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 this thing should be a parameter to it. There's a var name. It's actually not a variable name there, but it'll do. Okay, I think that looks all right. So now I want to pass in the var name as well. So I need the word type uint32t, and the word length is 4, and the var and the name there is CPU registers underscore arc.name. Oh, that didn't need that there, did it? It's just a blank line. And the header file should be very similar, but should just contain, say that it's an object. How do I define it in the header? What would be the correct definition for this? I should probably actually use that. Yeah, I'm going to use something like that. So I'm going to call this a def h code. And all we're going to do is we're not going to define the actual content, but just that it is a struct of that type. Like that. Name, and then the variable, which is a const, one of them. Yeah, I think that's right. So C code there. H code here. That's the name. Write the file name in the H code. Write the H code out. Oh, we also want to define a if the def CPU registers underscore center. so that we don't end up including it twice. Seriously, no idea if this is going to work or not. Generate C files arc32. C file is going to be C/CPU registers arc32. And oh, and the header file, so I've got to get the header file name as well, don't I? Header file as well, and then I should be able to do this but with 64. And then if we ever define something else, another architecture, we can always just shove it on the end and do another one, assuming it works, of course. Build, didn't work. Object cannot be interpreted as, oh dear, I think that's probably what that may actually be a Python 3 issue. Lines is not defined. Oh dear. Oh yeah, that's because that isn't defined. Yeah. Lines equals bracket bracket, and then we need to return lines as well. Right, I don't want to do it in the interactive mode. Don't indeed. Not all arguments converted during string formatting. Well, you're right. That isn't all converted. And that was at line 388. Done. Okay. CPU registers 32. We could do some blank lines there, but that looks right to me. Looks okay to me. I think that's sensible. Let's just put in some blank lines in there, just to make it a bit tidier. Run it again. So header file, there's the 32 one, there's the 64-bit one, and then the definition here. Type def struct, blah blah blah. And then it defines that there. And then we have, oh dear, no, we've actually put literal zeros into the file. Whoops. That's not going to work. /x00. I'm not sure why you didn't find that. /0 there. Oh, right. Yes, // I probably should have noticed that, but it was coming out as an oddity in the less output. There we go. That's better. And so they all come out as a string. Oh, I've missed commas off the end of all of these. All except the last one need commas. That's frustrating. So yeah, so what we'll do is we'll put a comma on the end of all of them, and then we'll take one off. Lines bracket -1 equals lines -1 without the last character. That's so tacky. Dot replace comma with nothing. It's more like what it should be. Right. Let's do that now and have a look at this. Yay! That looks cute to me. All right. This table here should be identical to the table that we've got in the file itself. Do you ever see? Do you ever look? Compare this one to this one. Show diffs. Oh, thank you very much. Switch my display. Oh, that didn't. It probably did work. It's just that the actual comparison is over here. Yeah, so there we go. All of that is comparing okay. Nothing's different except for the comments. Oh no, we have got differences in here. Oh, we've got differences because we've got lowercase rather than uppercase. Can I just make it uppercase just to make it easier for me to work with? If I just do that, it'll back into here. Yeah, so if I just change that to %x instead of that, there we go. Rerun that script, reload the file, and then, all right, now are we seeing any differences? No, the only differences we're seeing are the comments, and then we go into the strings here, and the strings should be identical. Yeah. Yeah, that's cool. I like that. I like that a lot. Awesome. Whee. Okay. So having defined that, we should start now be able to use it. So let's get rid of our tables here, because we don't need them. Default CPU regs 32 is not what we've actually got here. We're going to call it something else, and we can just import the files. So if not defined 64 and it is RISC OS, include CPU registers arc32 .c. Actually, no. .h. Sorry, I didn't include the .h file, don't I? I don't include the .c file because that will compile separately. Oh, lots of data all going away. And then if it's 64-bit, we do the same thing, but for the 64 file. And there's going to be a slightly different variable name that we're referencing. In fact, wouldn't it be better if we actually did default CPU regs there and then did a hash define? Define default CPU regs to be whatever it is in the header. That. And same goes for this one, but with the 64-bit version. Having done all that, do we think it's going to work? Build. It didn't work. Expected a semicolon inserted before. Oh, that should have been a T there, shouldn't it? Oh. Okay, so that's slightly wrong, but that's just my, yeah, that should be a const T there, and it should be a const, this is a const T there, so that's good. Rebuild that, and then build. Size of struct needed but not yet defined. Is that because it needs to be an extern? It's probably because it needs to be an extern here, doesn't it? Yeah, so I just need to put that into the Python as well to define it as an extern. Then we've got a legal cast to int. And I suspect that that's because this needs to be the address of that. That appears to have worked. Well, worked in the sense of it can link to it, but it hasn't actually done so yet. So all we need to do in here is to add in if ec build 64 one obj plus equals dear, I really can't type. CPU registers else build. Oh, no. Build. Oops, didn't mean to paste that. Don't know how to make CPU registers. It's right there. That's the string. How did I mess it up? Oh, O dot. Arguable that we don't necessarily need the O dot in there. I know that RISC OS Open decided to ditch that. But struct has no members. Semicolon expected, inserted before. Didn't include studint. Let's go do that in the Python code here. Not this bit, in the bit here that we need. Hash include studint.h. And so again. There we go. Run that. Yep, and then build. Trailing 0 for character 187. That is correct. Yes, because that's a jar that I'm not terminating. It's already been terminated. Cool. And if we build this for 64-bit as well, why can't I build it for 64 bits? Why have I lost my 64-bit? Oh, it was scrolling. Why did it? That's annoying. Oh, maybe because it's a small window it did that. Cast from integer pointed to integer gets correct because it's a register return. Cool. Hello, Helen Smithy. The register definition you moved to another file a few minutes. The 32-bit version seems to be the same width as the 64-bit. Or is it just double the length? You ask a very good question there. Yeah, so let's look at that now, just as you asked me. Yeah, so I've lost it. Where's the width gone? Width isn't there. Width. Where's my width gone? Here. Minimum instructions. No, this bit here. The minimum instructions for the width here. Sorry, Helen, I'm missing which bit is here. The register you the other files a few minutes ago. The 32-bit version seems to be the same width as a 64-bit, or is it just double length? So the size of the words, the int32, yeah, the int32 all of the definitions are still 32-bit, but the things they're referring to are 64-bit, and that's just because that's the way I've defined those words. That should be fine for most systems, I would think. The width of the ARC32 and ARC64 registers themselves are different, but they're defined differently. So if we have a look in here, so this is the, maybe it'd be nice to annotate this. This is the instruction length, minimum instruction length, maximum instruction length. They are always 4. So they'll be the same as well. I hope that explains it. I wasn't going to go and extend this. I could extend it to 64-bit, but then the table isn't quite as parsable on different systems. Hope that helps. Nice to see a new contributor as well. I don't usually get too many people on here, so this is quite nice. Right, so we've done that. We can now go and add some code. So I'm going to add the built files. And the reason I'm going to add the built files is because I don't want to run the generation each time. It will make it easier for me not to. And then we can do a bit more in the future. So here's the script that builds it. Here's the off-platform features. Let's update git ignore. So we ignore star.pyc. And that's everything. All right. So that should now build. Add generation code for the large tables of CPU registers. Oops. The CPU register dump information is defined in a table. Previously, this was a binary dump of generated values from RISC OS Pyromania. New tables if we wish. So one of the things we could do with this is you could actually generate a new table that had the APCS binding names in instead, if you really wanted to, and that might actually be useful for some environments. Or you could generate them with different ways of reference, looking at them. So you could have registers, the PC register at the top or something like that. You can reorder them anyway, is what I'm saying. This will allow us flexibility in the future. Okay. The tables have been checked in pre-generated so that they remain static and without intent. Okay. Okay. Good. Push that, and then you'll be able to have a look at the code and go, ooh, terrible Python code. Ooh, terrible Python code. One of the things that we noticed was that that didn't work when we ran it in Python 3. Yeah, float object cannot be interpreted as an integer. N words, 234. Oop, not that file, this file here, 234. Ah, that's division. We need it as an integer. Yeah, just make that an integer and we should get the same values. If we do a diff now, the only difference is that. So there we go. Fix Python code for Python 3, because everybody uses Python 3 these days except me. Just laziness and not having upgraded a lot of my code. Division needs to be to create an integer value for use in range. Okay, I'm going to push that as well. We'll just have a quick, oh no, that's not right, wrong window. I want to just have a quick look at it over here, and we can see whether it was passing its tests. Well, one lot's run and then a second lot here. So both of those should pass anyway, all being well. I don't think these take long to run. Oh, there we go, it's just finished. 1 minute 36 seconds, which is cute. And we just test it by loading it, don't we? Oh, we do actually run some tests. Yeah, that's right. Cool. Probably it would be nice to have this thing do a dump of the registers as well. Describe CPU registers. Or do we describe the CPU registers? I don't know. What does it actually do? That test code. Describe CPU registers. It does. It does actually describe it. So that has described the registers, and it's shown us that what we generated is exactly the same as what was there before. So excellent. I am happy with that. That's really good. Named no more. Not sure that's quite right. And again, dump offset should be zero. Should be zero. So that's okay. Quite handy, really. Yeah, cool. So that's working. Yeah, the other tests are all passing as well. So I think, given it's already 3:30, I think I'm going to call that a day with that, and say that we have actually done something useful. We've generated the CPU register descriptions in Python, so actually describing the data now, not just encoded into it, which is a bit better. What am I doing next week? Am I going to continue with this, or are we happy with it? Because we know that we're already at the point of having it stubbed. It's got to the. It's past its point of phase 2 being complete. We haven't got it quite to prototype yet. To make it a prototype, we'd have to define a bunch of functions that we could call that then had, for example, all the memory descriptions in it, the CPU info, and then all you'd need to implement would be just that part of it, and that would be what I would define to be a prototype, and then somebody else can come along and just populate it with those bits for particular hardware. And if it was there was a device descriptor, you'd use the device descriptor to say what the hardware type was. That's the way we'd go to if we were moving it to prototype. It's possible, given how successful we've been here, I may move these around and make phase 2 also include prototype as well. So we get a bit more movement on that in phase 2. Yeah. So that seems to be good. I'm not sure what I'm doing next week. Then I'll definitely be doing something, but I'm not sure what. I'll probably try to do. We'll do another module, certainly, whether it's this one or another one. I don't know, because we've got a lot of bits that we could do. If you have a look at the phase 1 work, there's a lot of little bits in this that haven't been completed. So CLI vector, I think that's going to be fiddly. FS commands is probably not that fiddly because it's just a set of calls into the rest of the system. I think that might be quite nice to do. OS pointer is only up to stub level, which is probably not too bad. Hardware, yeah, I don't really want to be doing the hardware. That's a bit of a pain, to be honest. I might do that separately. OS commands I've already done a bit of. Timer manager is, again, I want to get that quite complete, so I'll do that separately. Utility module is just star GOS, and that's actually quite fiddly to do, if I remember rightly. Yeah, it's probably quite hard to do that one. Ooh, I'm sitting in rather dark here, doesn't matter. And then video software is just a stub. Could do a bit with that. I just need to do some testing on TTX, and then I'll be happy with it. I just haven't got around to doing the testing yet. Ooh, but I did have something I wanted to show off. I wanted to show something off because if I have a look in the C code here, so OS platform features, right? So if we have a look down here, one of the things that is quite handy in RISC OS proper is that you can use hotkeys to go and launch strong help. And what you'd normally do is you'd be in your editor and you go and press your hotkey, and then up would pop a little window on the screen just showing you the help for that particular system call. So that would normally be what you do. So if you're looking at platform features, actually let's try OS read sysinfo, because it's more likely to have something there. So you go, oh, I want read sysinfo, and I'm looking at this one here. This is the chips and unique ID. So I want to look this one up. So I've got a hotkey now, Control Shift H, and then if I go over here, I can now see read sysinfo. We've dropped into there, and it's given me the links to the actual pages, the actual documentation. So I can see for chips and info, which was number 2, I can go to there and I can see this is the definition, which is a little bit more limited than the definition we have here, because there's a bit more information in there. But yeah, that's quite cute. I've now got hotkey lookups for the help, and it goes and launches it straight into my browser. Doesn't go and put it on over the top of my window with the content in it, but yeah, that's something we can look at later. Right, so I think that was all I wanted to say for today. We're good on what we're doing. Oh no, one other thing. Yeah, one other thing. I'm just going to witter for a bit here. I have started adding little sponsorship options to some of my projects. I haven't added it to the kernel introspection, and the reason I haven't added it is because I wanted to do it whilst I was here and I forgot. So let's do that. /funding. So this is a funding thing, so we're going to GitHub funding, and this just says enable this. Platforms we can sponsor with on GitHub. So git add.github/funding. Add the funding sponsorship button. This says where the sponsorship should take you. So we now go and push that. Done. And then we go over here and reload the page. We now get to sponsor this project, and you can sponsor me if you want to. And the reason I'm doing the sponsorship thing is because a lot of people have made comments about the fact that they don't actually want to be involved in any of the coding or anything, and they can't because they don't know enough. But it would be useful to have some way to be able to support things. So that's what it is. So you can click on the sponsor button and it does something. And it talks about me and what I'm doing, and then you can select tiers, any particular rate you want, or you can choose one-time contributions. And yes, they're in dollars. I'm sorry, I can't change that. I don't know why, but I'm assuming GitHub. Although strictly, since GitHub is Microsoft, we can now curse Microsoft for this. Back to the old days, yay! Yeah, I mean, there's a lot of things to curse Microsoft for. But maybe just using dollars isn't the best of them. Anyway, I am done. I'm going to try and fall asleep now, I think. Well, not try and fall asleep. I probably will fall asleep at some point. after we've done a few things this afternoon. Nice to see people here today. Happy New Year to everyone. Merry Christmas. Hope you had good holidays if you weren't celebrating Christmas, but had a good break if you did. I shall be back next week. Don't know what I'm doing. We'll work something out. If anybody has any thoughts on the matter, please do post to the RISC OS open forums. I'm going to click on the link here and take you to the page, this page here. So go and leave comments on here, and if you've got any ideas for things we should do, but I am focusing on the RISC OS 64 stuff. Thanks very much, and yeah, have a good 2026. I'm still getting used to it. See you later. Bye.